is Vacuum, which is a new set of tools for visualizing structures in a heap, using GHC's heap live. And I want to demonstrate how that works by showing how it works on these adaptive data structures that I've been working on for the last couple of weeks. We have some guys working on here at Hackathon that specialize in polymorphic container types with unboxed representations, and you can really see that in the tool. So, so just to get a sense, Vacuum is built on top of a new primitive that GHC provides for the GHCI debugger called unpack closure. Turn on some extensions. Okay, so it's got a really amazing type. This is a very deep magic. For any A, it'll give you a pair or an unboxed pair or a triple of the pointer to the closure, I think, an array of values that are stored in the closure, and a byte array that represents the code. I think that's how it works. And this is good for the debugger because you can step through values and then hit and see what's in scope and look at things being evaluated live. But it's in a sense an arbitrary reflection in the heap, so you can do some really cool things like visualize. Now Matt Morrow wrote a tool, Vacuum, that takes this at the bottom and reflects the data structure into a proper graph structure. So the pointers become edges and the values become the data stored at each node. And then you can print that out with graph tools like dot and graph.viz and render them. And I wrote an interface in front of that operates for GHCI called Vacuum Cairo. So if we import Vacuum Cairo, it gives this function. So for any A, it doesn't do A. The type doesn't tell you much. But
it's like F#.
Yeah, there we go. So that's X mode can handle this. Okay, so that was one. And we can do a few other things. View a pair, for example. And that's exactly what's in the heap right now. There's an object with two pointers pointing to the nodes. So you already, I think, one good use of this is for teaching data structures because it really clearly shows what happens. Here we wrap the pair in a box, and so we now have an empty list, or it's a list of one element where the element is a pair. There's our cons node, there's our pair node, and there's our empty list constructor. And we can start to see all the indirections involved in representing Haskell data. So the list, you can see there's our nice spine of the list and all the elements hanging off. I think list comprehensions look really beautiful. If we take a list and y from x to triple, you can see the sharing. So that's two things you can do if you view the heap directly. You can actually see operationally where the sharing is taking place. You can see the unboxing, which you can't see if you're just doing a show on the data structure. Show has to button the thing out and remove all the sharing. You can actually observe the sharing, which we see here. Where we floated out, see the bindings to X here are now shared, and you actually see multiple pointers to the element stored in the heap, along with our lazy spine here. And of course, this has to evaluate the whole thing to show it. It doesn't support looking at a thumb to see if it's unevaluated.
Well, in principle, it does now.
It does now?
Well, sort of. So you can say you don't look much, and the other problem is sometimes you have an undefined and that kills everything.
Yeah,
but
exactly.
I think that fixed that in the latest library.
Yeah, so we saw.
Cool. Can I just quickly check? Is it possible to drive evaluation one step at a time with this?
So is
I
there?
don't think so.
I mean, so whether it's evaluated or not.
I'm not hearing whether
Well,
it would
you
be
could
possible
assume
to
you
write
can do this because the debugger can do
Yes, you
this.
just step the debugger renewed. If it doesn't force things itself, then you
You
step
can
the
stop
debugger.
and say.
So you could actually use this to generate an hash trace file that works for all anything GHC can compile.
Yeah, I mean, whether it's evaluated or not, it's the bottom bit on the pointer to the closure, isn't that right, Alexi?
Whether it's
There's a eval bit on the bottom of the pointer. Is this evaluated yet? Or not?
Yes, you can look at that.
Yeah,
You can look
so
at the
that's the
pointer,
thing
but
we need to
you
test.
can't look at the info table as well.
Yeah. So as long as presumably we can do that.
Yeah.
So that's how we would decide not to evaluate any further. So I just wanted to show a few more things. It's nice having defaulting actually in GHCI here. We can just compare. You can see there's a little bit of a refresh bug here actually. I'm not sure whether it's flexible or higher. But there's our Justin and then the pair and these guys hanging off. And I want to look at some of the container types because I think besides just teaching basic data structures, which I think this is good for getting a sense of how the data is represented and all the pointers involved, it's really helpful for advanced users who are designing a data structure. So we had our list here. There's obviously a lot of pointers involved there. We can look at arbitrary structures, so a map. And there's a map is a size-balanced binary tree with bin nodes which store the size at that node.
Yes,
the
the size, key value, and left to right.
Yeah. And then so we see here's the key, the value, the left and right child. The key and the value, obviously it's a polymorphic data structure, so it has to be represented uniformly, the A, the K, and the V components. So they're just pointers to some value. They're not unpacked, there's no special representation involved. The depth is an int, I think. So that is unpacked and stored in the constructor. So we save one pointer for things. And we also see how the tip is shared between all, there's only one tip node allocated, which is quite interesting. And it's just shared. Well, I guess there's only here.
The formatting you see for the bin nodes, is that generic or did you write this specific formatting for the map?
This is generic. Yeah.
Okay.
It pulls apart the closure into a list of unpacked values that are stored inside the constructor, and then a normal pointers.
Right.
They're separate. So if you make a 10 value constructor where all the values are unpacked, you'll see a list of 10 values there.
So those sizes are with a van in front of them?
And
Yes, and an unpacked.
Right.
Yeah. So these are monomorphic data types that have had unpacked strict fields applied. So it works that unpacking, which saves us a pointer and gives us better density, works for any single constructor data type.
Yeah.
So it won't work for some types like just and nothing.
Okay.
And it won't work for recursive types. But it will work for int and double and all the ones we care about.